Hello, everyone, and welcome to our first practical video. In this one, we will start a series of exercises to apply what we have learned on the topic of empirical energy models. And the software that we will be using is the one that we recommended in a previous video, the software named Gulp. And today we will start with the first exercise. I believe each exercise will take a couple of videos. We will not finish it in one video, instead over a series of videos. And some of the input files and the problem statement itself will be posted in a link in the description of the video. So, all right, so let's get started. We are doing exercises on empirical energy models. And in fact, all the exercises we'll be doing on this topic, we choose a model system which is FCC Platinum. So we will investigate finding the equilibrium Latz constant and cohesive energy for face-centered cubic platinum using two empirical energy models, the Lennard-Jones potential and the embedded atom method. Of course, one of these, because there are several of them, depending on which research group developed which potential. We will do this task twice using an automated fashion and a second approach using manual search. And of course, we will go into the details of how to do this. The code that we will be using in this exercise is Gulp. So that's really the first problem or the ideas of the first problem. But maybe it's actually wise to point out what do we mean by FCC Platinum and also highlight another useful software that we will use for visualization purposes. It's actually called VESTA. This can be easily obtained for free from the developer's website. So if we just type VESTA visualization, we can go to the developer's website. There are versions compatible with Linux, with Windows, and I believe with Mac as well. So this is an overview, and it reads several formats as well. I strongly recommend using this one during our first exercises on the empirical energy models. Of course, we will be using other software packages as well for visualization. This one is free and nice. It brings it shows some very nice visualizations of the crystal structure. At the same time, let's go as well to the input files provided for this problem. We have three input files, one called platinum.lennard-jones.input, platinum.embeddedatommethod.input, and platinum.cif, which is a visualizable file with VESTA. So let's open a terminal here. I can call VESTA from where I installed it. This is on Linux, of course, on my virtual machine here. So software VESTA and then VESTA again. So that opens the graphical interface, which I can use to open platinum.cif, right? And if I do this, that's the FCC platinum the FCC crystal structure, and these are platinum atoms, and I have only one unit cell. All right, so that's really the material we are gonna study in this first exercise. Okay, so let's go back to the problem statement. The first thing we are asked to do is to calculate the equilibrium Lutz constant and total energy in electron volt for FCC platinum using the supplied Lennard-Jones potential and the automated energy minimizer algorithm in Gulp. So make sure that the opti keyword is used, and we will go over this now. We strongly recommend consulting Gulp online manual. So there is an online manual here. If you click on this link or simply just type Gulp simulations, you will actually reach to this manual. It's very detailed. It's by keyword or option in alphabetical order. You just click on one of them and read the details. You don't need to do this right now, but as you use the software more frequently and start looking at options, this will be very useful. And another thing I would recommend, if we go back here in the help, oops, I think it's better to go from here, Gulp simulation software. Another useful utility in Gulp is if you click help here, there are actually a lot of examples provided with the software. So about 70 examples. So these, in addition to the exercises that we will do, will be very, very valuable tool in learning this software for your own interest. So let's go back to the exercise. And then what? Note that the Lennard-Jones potential used for platinum in this study is taken from the 2008 potential of Heinz et al. And this is the paper that actually developed this potential. And I believe we actually discussed it briefly in one of the previous videos. Okay, so let's now get into more practical stuff. We will go to the virtual machine here. The input files provided for us, and I can actually close VESTA, at least for the moment. Okay. Let's look at platinum.Lennard-Jones, and that's really how an input file in Gulp looks like. It's very simple, very straightforward. So let's actually try to explore what do we have here. So usually the input file of Gulp starts with a line at the beginning that define what kind of calculation that you want. And we are using here 3 words, opti, constant pressure, and stress underscore out. So opti really just means you need to do energy optimization. So you need to optimize the structure. And to do this, you have 2 options, either constant pressure, CONP, or constant volume, which is CONV. Now, if you do constant volume optimization, so if you fix the volume of your crystal, then really the only option you can have is just to move the ions or the atoms inside, right? But you will maintain the volume and of your crystal. Now, constant pressure is more flexible because maybe the starting size or volume of your cell is too large, so it can actually shrink during the optimization, or it was small, so it can increase in size, and so on. Finally, stress underscore out is a tag or a keyword that simply tells Gulp, please calculate the stress, and print the stress out. By the way, in this calculation, we are only using 3 major words here. And if we go back to the Gulp manual page, and I think which we did stop. Did we stop? No. I think it's the second one. Yeah. If we go here to the manuals, online guide to commands. So you see, it's the keywords in alphabetical order. So the constant pressure, the opti, and other, and these keywords were taken from here. The rest of the options are given in the second block of the options of Gulp, as you see here. So let's go back to our input file, which as we said, we will provide these in a link beneath the video. The first option here, or the next option after you define the type of calculation, is really defining the geometry of your simulation box. So by the way, you can write comments if you want here inside. This is, you can write your own comments here with a hashtag sign. So you can say that this is just type of calculation, and so on. So the input file is kind of flexible on what you write, and provided, of course, that you put something like a hashtag here to indicate to the software that this is a comment. Okay, so let's continue our analysis of the input file. We have a block here that's cell, followed by 6 numbers, 1, 2, 3, and another 3 numbers. When you say cell to gulp, that means that you will specify the geometry of the cell using lengths, so A, B, C, and angles alpha, beta, and gamma, with the convention that gamma is between AB. So gamma between AB. So this is your gamma angle. Also, we can actually do this on a bigger drawing here. So again, if suppose this is your origin, this is your A axis, your B axis, and your C axis. So between A and B, you have gamma. Meanwhile, between A and C, you have beta. And finally, between C and B, you have alpha, right? For FCC crystal structure, the lengths ABC are equal. And by the way, the units here are the default are in angstrom. So the ABC are equal. We just gave an initial guess, which is 3.8 angstrom. Of course, you can make a better guess by consulting experiments, for example, or asking, maybe we will test this in the exercise. You can also ask some AI tool, whether a vanilla one or a one that's trained on materials. But, let's see what's going to happen here. So I have ABC, 3.8 angstrom, and the angles alpha, beta, gamma. This is a cubic structure, it's 90 degrees, all of them. Next block is defining atom positions. And as you see in the FCC crystal structure unit cell, there are 4 atoms. But before this, there is the option word here, fractional. And by the way, Galb can accept also Cartesian. So if you write cart, you can insert these coordinates in Cartesian, but fractional is the one that we prefer until in a later exercise where we will show when Cartesian becomes useful. The syntax is very simple. You just put the symbol of the atom, for example, PT, 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 and then the XYZ coordinates in fractional. So 0, 0, 0, 0, half, half, and half, 0, half, and then half, half, 0. A couple of points to point out here. One question is, where do you obtain these atomic positions? Well, if it's a simple crystal structure like FCC, then it's really straightforward. You just, look up any standard textbook on material science, and you will know that in FCC there are 4 atoms per unit cell, and these are the fractional coordinates. If it's a more complicated structure, then you need to download it from a database. And there are many useful databases you can actually check. You can check, for example, by typing crystal structure database. There is this crystallography open database, right? There is actually one dedicated, for example, for crystal structures of drugs, right? For molecular crystals, the CCDC. There is also there is the protein data bank. For example, this is for protein crystal structures, obviously. There is what else? There's the materials project, which is a very nice project that contains a lot of useful information about mainly inorganic materials. Again, it has a lot of crystal structures in it. So that's your source of how do you bring crystal structures. So that's one comment. Let's go back to our input file here. Another thing is, wait, there are 4 atoms here, but if you remember our VESTA visualization, let's actually close this for a second. Close without saving. Fine, no problem. Let me delete these annotations for a second here. If you remember, let's open VESTA one more time. Software VESTA. We can also release the terminal. And if we open this, platinum.cif, so you see seems there are more than 4 atoms here, but in fact, there are 4 only. What you see here is just repetition under periodic boundary conditions. And actually, if you look, VESTA brings out the 4 atom position. You see down there, the 4 atom positions, but the rest is just a repetition. For example, this one, let's highlight it maybe. This one is the same as this one, but they are just repeated under periodic boundary conditions. To see this or to convince yourself, there is a very nice option here in VESTA, which is the boundary. Of course, you can go X max and Y max and Z max, make them 2, 2, 2, 2, and that gives you a supercell, right, of platinum. So this is like 8 cells of platinum. I can go back again to this boundary and make this 0.99. Surprisingly, it accepts a fractional number of lengths of vectors. So that defines the vector, the length of the vector of the cell. So if we apply this, you see 4 atoms. So there are only 4 atoms. But where are the other guys? Where did they go? They just have been disappeared because I stopped at O. So I asked it to stop at 0.99 of the cell vector in A and B and C. So that means that this is supposed to have a periodic image here and a periodic image here and one here and one here and one here and one there. Look, it's all this atom. Similarly, let's take another one, which may be this one. This one has another one in front of it, right? So these are periodic images. Also, this one, the one in the back here, has one in front of it here, right? Finally, the one at the bottom here has also one on the top that corresponds to it. So these define the faces, right? These are the face atoms. So let's delete all of this. I hope this convinces you that there are 4 atoms only in this cell. We can close this actually, in fact. Save change. Nope. So yeah, the terminal is released. So let's go to our input file one more time. So after that, there is a species block that you see here, where you need to define what the kind of species that you have. By the way, you have to make sure that the English is written correct. So there is the word species, it's written the spelling is correct. Otherwise, this will generate a gulp error, as you can see, as you can actually observe in your calculations. What you need to specify is the symbol of the element. Specify it's a core or a shell. Remember the shell model that we discussed with the video on Buckingham potential. So you need to specify, are we talking about a core or a shell? Generally, everything is considered core except when you have a potential, very specific cases where you have potentials that have shells as well. And I think we will have an exercise on this as well. Does it have charge? No. In this Lennard-Jones representation of metals, there are no charged species. Pretty much everything is neutral. And then Lennard-Jones potential. The next block defines the Lennard-Jones potential. In fact, gulp comes with a huge library of available potential. So the way you tell gulp that I want Lennard-Jones is to specify the word Lennard and the exponents 12, 6. You might tell me that this is the default of Lennard-Jones. Why do I need to specify it? But the reason is gulp actually gives you the option to specify as many potentials, as many exponents as you wish. You can put 9, 6, 11, 5, 13, 7, whatever, as you wish. Okay. And then what? And then first atom, second atom. So this is atom number 1, atom number 2, a parameter called A, a parameter called B, the minimum cutoff, and the maximum cutoff. So let's explain this. Platinum core, that's simple. I'm telling gulp this is the interaction between platinum and platinum. What are A and B? We are used to the Lennard-Jones, V of R, Lennard-Jones potential as 4 epsilon And then there is this sigma over r raised to power 12 minus sigma over r raised to power 6. So where are the epsilon sigma? There is actually an option to give Gulb your parameters in terms of epsilon and sigma. But I actually, in this input file, I used the more sort of a default option of Gulb, where pretty much I have the potential written as A over R to the power 12 minus B over R raised to the power 6. So that means that A, if you do the algebra, that A is just 4 epsilon sigma 12, and also B here is what? Is 4 epsilon sigma 6, right? So that's basically what are the A and B? It's just the lumped parameters of in terms of sigma and epsilon. What are the units? Well, standard units, this is electron volt, this is angstrom, and that automatically, if you see here, that means that A has to be in what? Electron volt angstrom raised to power 12, and this has to be in electron volt angstrom raised to power 6. It's just simple algebra here. Where did I get these parameters? From the paper. Remember the paper that's written here in this physical chemistry paper, right? So this is where we obtained the parameters from. What else do we have? R minimum and R maximum. In fact, in the previous videos, we discussed the cutoff. And it is actually R max, the one that we discussed. You remember, this is V of R versus R. The potential looks like this. You are not going to calculate all the way to infinity. You stop at some cut. That's what Gulb defines as your R max, right? And the value of 12 angstrom here is just taken again from the paper. This is the recommendation of the paper, to take it as 12 angstrom. What is R minimum? It's some sort of a flexibility that Gulb gives you. Gulb just gives you the flexibility to define a minimum cutoff. So, for example, you say below certain R. So let's say suppose we make this one angstrom. So below a certain R, there's no interaction. It's just a freedom, flexibility. It's rarely used. It might be used specifically in some studies on radiation damage, for example, where the very, very low regime of distance is very important, but otherwise nobody really uses it. And the default, by default, you can set it to 0. Suppose you forgot this information. How do you retrieve them back again? Your go-to place is the manual. Simply search for the keyword or the option Lennard, Lennard, and that's where you find it. Yep. So you find all these details that we discussed described in the manual here. That's supposedly if you forget something, if we have some of the details that we described here. Okay, so finally, the last thing, and it's pretty much optional here. You don't have to do this. The last thing is I'm asking Gulb to output the final structure in CIF format. So it's the word output, and I'm requesting CIF format. Gulb gives you a lot of freedom here. You can request XYZ format. You can request CFG format read by Atom-I software. You can even request BDB format, I believe. Not 100% sure of this. The protein data bank format is kind of flexible here. And then you give some name for that file, for example, platinum.cif. So that's a sample input file for Gulb. Let's save this for a second here and close without saving, or save. Yeah, let's save, no problem. In fact, I will do a test case here. So let's open a terminal. I will make a directory and I will call it test, and I will go to the test folder. I might actually copy platinum .lg here. And I will modify it really slightly to show some difference. I will, instead of opti, I will use the word single. And the word single here is very, has a very specific and simple job. It tells Gulp, please take the structure and calculate its energy. Don't do anything else. Don't optimize, don't move atoms, nothing. That's it, as simple as this. So let's save this. And let's highlight what's going to happen here. How do we use Gulp? Let's call it from its place. On my laptop, I put it in my home folder. It's in software, Gulp. I have actually a couple of versions, so I'm using 6.2 here. And the binary is called Gulp. And then the name of the input file, I put this less than sign, platinum.lennard-jones.in. And I'm requesting some output. By the way, you have a complete freedom in Gulp in choosing whatever name of input file. Same thing for the output. In this case, I will call it output.single because I'm doing single calculation. So let's hit enter. Well, it's run and it's complete. We do have an output file here. It's called out.single. I can open it and see what do we have. So out.single. First of all, it acknowledges the developer of the software, Professor Julian Gale at Curtin Institute for Computation. This is version 6.2. This version actually goes back to December 23. It summarizes your input. So I'm doing single calculation, constant pressure. We are printing the final stress tensor, right? The job started on May 8, 2025 on one processor. By the way, Gulp can run on parallel and several cores, but we are not using this utility here. Our formula, our chemical formula is platinum 4 because it's platinum made out of 4 atoms. Number of reducible atoms, 4, right? Total number of atoms is 4. You might wonder what's the difference. Sometimes because of symmetry, your irreducible atoms is less than the actual atoms. But for us here, they are both the same. Dimensionality, it's a 3-dimensional structure. It's a bulk structure. And of course, periodic boundary conditions automatically applied. Here, Gulp revise the geometry of the cell. And remember, there are 2 ways to specify geometry. Either 3 lengths and 3 angles, as we did, or you can define 3 vectors. So this is like vector A, vector B, vector C. And this is the X component of the first vector, and this is the Y component of the first vector's Z component, and same thing for the other 3. So this is like BX, BY, BZ, and because of the simple cubic symmetry, if it's a vector in B, there is only Y component, the others are 0, and so on and so forth. So these are 2 ways to write the same thing, right? So nothing really fancy here. What else? It calculates the volume of the cell in units of angstrom cube. The default temperature is 0 Kelvin. The default pressure is 0 pressure. So we are not doing temperature stuff here. This is just 0 temperature energy calculation. It revised the fractional coordinates of every atom. So platinum 0, 0, 0, platinum 0, half is half. There is no charge. Charges are 0. Occupancy, that we will not discuss. This is something of interest to mineralogists and those who study some complicated materials where atoms could have some fractional occupancy. For us, everything is just integer 1 occupancy. What is the some physical details about the atom? And by the way, these are from the standard Gulp library. You don't need to modify them again, except you know what you are doing for some reason. So this is platinum. It's a core atom. Its atomic number is 78. Its mass number is this. We didn't specify these numbers, but they are coming from the library of Gulp. and this is the charge. Some radii, covalent, ionic, and van der Waals, and that's it. It also mentions that it will use Ewald sum for electrostatics, 3D electrostatics, or Parry sum for 2D, or Saunders sum for 1D. In fact, we will not use any of them because there are no charges in our simulation. Let's skip these details. This is our Lennard-Jones potential. This is the parameter A. This is the parameter B. These are the units. These are the exponents, 12, 6. And this is the minimum and maximum cutoffs, 0 and 12 angstrom. Gulp calculated the total energy of the structure. It's minus 11.13 electron volt. We don't know if it's the minimum energy. Remember when we discussed energy landscapes, we said usually you start your initial structure somewhere here in the energy landscape. So this is energy versus some generalized coordinates. And then your optimizer will help you to go down. Remember here, we aren't really gonna go down because we are doing single calculation, remember? So there is no minimization here. If you change single to opti, you will go down to some minimum structure, local minimum. The total energy is minus 11.13 electron volt, which is in units of kilojoule per mole is minus 1074.3 kilojoule per mole. How much RAM memory if your computer it used about 2 mega, so not too much. Timing analysis, calculation of real space energy and derivatives. This was very, very quick. It's a fraction of a second. Total CPU time, it's like 0.02 seconds. It's really nothing. So congratulations with this. We have done our first atomistic simulation. We will stop here, and in the next video, the first thing we will start with is what happens if we run opti calculation. We ask to optimize the structure to go to the deep local minimum. What's gonna happen? So that will be the question in our next video. Thank you so much, and see you in another video.